So the way that a lot of you were attempting to do number 29 was really digging into example 9.1, which is great. And I think a lot of the confusion was actually coming from example 9.1 more so than problem 29. So I want to walk through example 9.1 and talk about what's going on there. So in example 9.1, they say from section 8.5, we know that the sum of our x sub i's minus our mean of our samples, the squared, is going to be equal to, using the population mean in there, so we've got this x sub I minus the population mean squared minus n times the sample mean minus the population mean squared. Now, you can find this on page 244 if you want, where they actually showed that those two things are equal. You don't actually have to dig into that too much though. Example 9.1, we're just going to use that. And really, we're just allowed to use it because we saw it in section 8.5. And again, if you want to dig into it, it's there on page 244. Now, I also wanted to draw attention to corollary 8.1. That tells us that our sample variance is equal to 1 divided by n minus 1 times the sum of our x sub i's minus our x bar squared. And while we're making a list of things that are going to be useful to us along the way, I wanted to remind you that the population variance, the way that we defined that is it's the expected value of x minus our population mean squared. A lot of you were digging one step deeper than that in how we would find that expected value, but we don't actually need to go deeper in that definition. So if we're going to find our expected value of our sample variance s squared, what we're doing is we're going to apply corollary 8.1, and we're finding the expected value of 1 divided by n times the sum of our xi's minus our x bar squared. Now, using that equality from section 8.5, what we're really finding is the expected value of 1 over n, and then replacing our sum with this sum of our xi's minus our population mean squared minus n times x bar minus our population mean squared. So we want to find that expected value. Now, going back even further before chapter 8 stuff, using section 4.3 where we looked at stuff about expected values, 1 over n minus 1 is a constant. So the expected value of a constant times something is the same as that constant times the expected value. And we saw in section 4.3 also that if we had a sum of things that we were taking the expected value of, it was the same as taking the expected value of each of those terms in the sum and adding them together. So in doing that, using those ideas from section 4.3, we get to absorb that expected value in all the way inside of the sum, leaving us with 1 over n minus 1 times the quantity of the sum of the expected value of x sub I minus our population mean squared minus n times the expected value of x bar minus our population mean squared. So now, if we take a look at definition 4.3, we have some things that look a little bit like that population variance. So using definition 4.3, we get to rewrite this as 1 over n minus 1 times the sum of our variance of our xi minus n times the variance of our mean. Now, a couple of things to note. The variance of the xi equals the population variance, and the variance of the mean is variance divided by n, that population variance divided by n. You can see this on page 233 if you want to dig into that a little bit further. Now, that means that we can rewrite all of this as 1 over n minus 1 times the sum from 1 to n of our variance minus n times our variance divided by n. Now, our sum of our variance, when we're taking the sum of the same thing over and over again, so the sum like from 1 to n, that's taking n many of these things and adding them together. Another way to write that is writing n times the variance. So that allows me to replace my sum with n times the variance. And I did the n times the variance divided by n, those two n's canceled out, so I have n times the variance minus the variance. Now I can notice that I could factor out the variance and I end up with 1 over n minus 1 times the quantity n minus 1 times the variance. Well, my n1 minus 1's cancel out, and I'm left with just the variance. Now, this is the conclusion that example 9.1 comes to, and it says that it's an unbiased estimator as a result, because we have the expected value of our sample variance is equal to our population variance. Now, jumping into question 9.29. They've defined the sample variance in a new way now. Instead of dividing by n minus 1, they're going to divide by n. They wrote it in this way, and I'm going to rewrite it so it looks more similar to what we see in example 9.1. So it looks like 1 divided by n times the sum. There's no difference in these two things. Now, what we did in example 9.1, we used the variance where it was 1 over n minus 1, because that's how our sample variance was defined for us. And now it's being defined with 1 over n. So a hint that I was giving to a lot of you in class was, how does that dividing by n make it different than example 9.1? And a lot of you were actually making it more complicated than it is. So if we look at this part right here, the sum part, it's the same as example 9.1 if we ignore the 1 divided by n minus 1 that's out in front. So we're going to use that. So if I want to take the expected value of this variance that I have here, using all the steps that happened in example 9.1, I can get to the point where I know that I'm basically replacing the 1 over n minus 1 out front with a 1 over an n out front. So I'm basically going to skip ahead to that last and final step where I have 1 over n minus 1 times the quantity n times the variance minus the variance in our example. And I'm going to look at it when I have 1 over n times the quantity n times the variance minus the variance. This is the difference that'll happen between example 9.1 and problem 9.29. So then when I do this, again, I can factor out that variance. So I get 1 over n times the quantity n minus 1 times the variance, which is just n minus 1 times n, or n minus 1 divided by n times the variance. And that's what I'm asked to show, actually, in number 9.29 in that problem. And in doing so, what I've shown is the expected value of this sample variance is not the same as the population variance, so it is a biased estimator. And that's all there is to this problem. So a lot of you were making it a lot more complicated. What you really needed to do was just say, hey, by example 9.1, I know that it's this when the population or the sample variance is equal to this, and this is the change, and so here's the result of that change. And you would have been done. So hopefully that makes sense and gives you a little bit of an idea of like how to do these things, and hopefully takes you down memory lane a little bit with some of the stuff that we've done in class.